Sometime around 250 BCE, a craftsman in the ancient city of Ctesiphon sealed a copper cylinder inside a clay jar, inserted an iron rod, and poured in a solution of grape juice or vinegar. No one recorded why. No ancient text describes the intended function. When German archaeologist Wilhelm König unearthed this object in 1936 from a dig site near modern Baghdad, he held it in his hands for a long time before writing, in a paper that the academic community largely chose to ignore, that it bore a striking resemblance to a galvanic cell, a battery. Reconstructed versions of the object reliably produce between 1.1 and 2 volts of direct current. Alessandro Volta would not invent his electrochemical pile for another 2,000 years. What the Baghdad battery was used for, electroplating gold onto silver artifacts perhaps, or something we have not considered, is less unsettling than the implication of its existence. Not that ancient people stumbled onto electricity, but that they may have understood it, applied it, and then simply moved on. The knowledge did not die. It was never written down to begin with. Few materials in the history of engineering carry a more humbling reputation than Roman concrete, known as opus caementicium. Modern engineers constructing the seawalls of major ports around the world, Dubai, Singapore, Miami, operate on the assumption that their structures will require significant repair within 50 years. Roman breakwaters submerged beneath the Bay of Pozzuoli since roughly 37 CE are not degrading. According to research published in the journal American Mineralogist, they are mineralogically strengthening. When seawater penetrates the ancient concrete, it reacts with the volcanic ash the Romans used as aggregate, a mineral called philipsite, and grows crystalline structures that fill existing cracks rather than widening them. Modern Portland. Cement. The foundation of every skyscraper, every highway, every dam built since 1824, does the opposite. It erodes. Roman engineers apparently knew something about the chemistry of pozzolanic ash that we spent roughly 19 centuries forgetting. What other material knowledge was lost in the same silence? In 1901, sponge divers surfacing from a wreck off the Greek island of Antikythera hauled up what appeared to be a badly corroded lump of bronze. It was catalogued, assigned a number, and stored in the National Archaeological Museum of Athens, where it sat for nearly 50 years. When historian Derek de Sola Price applied early X-ray imaging to the object in 1951, he found a mechanism of extraordinary complexity, at least 30 interlocking bronze gears, differential gearing systems, and engraved annotations, capable of predicting solar and lunar eclipses, tracking the metonic cycle, and displaying the positions of the known planets on any given date. Researchers at University College London reconstructed it in 2021. They needed computer modeling tools that did not exist until the 21st century to decode a device built in the 2nd century BCE. Mainstream consensus describes it as an anomaly, a singular genius that left no descendants. But anomalies, by definition, are things that do not fit the pattern. The more honest question might be, what pattern are we working with, and who decided it was complete? Standing in the courtyard of the Qutb Minar complex in Delhi since approximately 375 CE, a 6.7-meter iron pillar has done something metallurgically inexplicable for 16.5 centuries. Nothing. No rust. No significant corrosion. Standing exposed to the monsoon rains of northern India, cycling through humidity levels that reduce modern rebar to orange powder within decades, the pillar remains largely intact. When scientists at the Indian Institute of Technology analyzed its surface in 2002, they found a thin crystalline layer of iron hydrogen phosphate hydrate, a compound that forms a passive protective film and prevents further oxidation. The phosphorus content of the pillar is unusually high, suggesting the ancient smiths used a specific smelting technique that produced this effect deliberately. Whether they understood the chemistry or discovered the outcome empirically, they achieved a result that the modern steel industry, with all its controlled furnaces and spectroscopic analysis, has struggled to replicate at scale. The pillar simply stands there, absorbing the observation with the indifference of something that has outlasted every dynasty that claimed credit for it. In 1993, a German robotics engineer named Rudolf Gantenbrink sent a small wheeled robot called UPUAUT-2 through a narrow shaft in the Great Pyramid's Queen's Chamber. Among the readings the robot transmitted back was a temperature measurement, 68 degrees Fahrenheit. Researchers who followed up on that figure found that the interior of the Great Pyramid maintains a near constant temperature of 68 degrees Fahrenheit, regardless of the desert heat outside, which regularly exceeds 100 degrees. 68 degrees Fahrenheit is precisely the average temperature of the Earth's surface. Whether that is a meaningful coincidence, an intentional engineering target, or simply a byproduct of the pyramid's mass and geometry is not something mainstream Egyptology has thoroughly explored. What is worth noting is that achieving passive thermal regulation at that scale, without mechanical systems, without insulation in any modern sense, represents an engineering challenge that contemporary architects of large public buildings still find formidable. If the pyramid was merely a tomb, the temperature consistency is an elaborate accident. If it was something else, nobody has agreed on what. At an elevation of over 12,000 feet in the Peruvian Andes, the Incan fortress of Sacsayhuaman contains blocks of limestone weighing between 100 and 200 tons, transported from quarries as far as 25 miles away, and fitted together without mortar along joints so precise that a sheet of paper, much less a credit card, cannot be inserted between them. The largest single stone in the complex is estimated at 360 tons, heavier than a fully loaded Boeing 747. Spanish chroniclers who arrived in the 16th century reported that the Inca themselves described the walls as the work of a prior civilization, built in a time before memory. Modern experimental archaeologists have demonstrated that the stones could theoretically have been moved using wooden sledges, earthen ramps, and thousands of laborers. What they have not demonstrated is how the fitting was achieved. The millimeter precision joining of irregular polygonal surfaces across thousands of contact points, at altitude, across an entire fortress. Acceptable theories remain on the table. Demonstrated methods do not. Around 672 CE, during the Arab siege of Constantinople, Byzantine naval forces deployed a weapon that altered the course of the engagement in ways that the Arab fleet had not anticipated and could not counter. Greek fire, as it came to be called by those who encountered it, was a liquid or semi-liquid incendiary projected through bronze siphons. According to accounts from both Byzantine and Arab sources, it burned on water. Attempts to extinguish it with sand or seawater reportedly intensified it. Some accounts describe it reigniting after being submerged. For nearly 3 centuries, it was decisive in at least 5 major naval engagements that preserved the Byzantine Empire. Then Constantinople fell in 1453, and the formula disappeared entirely. Historians have proposed various reconstructions: naphtha, quicklime, pine resin, but none of the proposed formulas reliably reproduces all described properties. What is not in dispute is that a medieval civilization possessed an incendiary technology specific enough to function under conditions that no modern researcher has been able to fully recreate. The secret was not lost through carelessness. It was protected so aggressively, according to Byzantine records, that no single craftsman knew the entire formula. The knowledge was partitioned, and when the empire ended, so did the parts. Beneath the surface of the Nazca Plateau in southern Peru, a network of underground spiral wells and aqueducts called puquillos has supplied water to the driest desert on Earth for an estimated 1,500 years. Some of them are still functioning. What Italian astronomer Rosa Lassaponara and her colleagues reported in 2016, after analyzing the puquillos using satellite imaging, is that the spiral openings were engineered with specific orientations to capture seasonal wind patterns and drive air pressure through the underground channels, moving water through the system without any mechanical assistance. The precision of the orientation angles across dozens of separate structures suggests systematic knowledge of fluid dynamics, wind behavior, and subsurface hydrology, disciplines that we tend to associate with 17th century European science at the earliest. The puquillos do not merely work. They work because someone understood, in rigorous and reproducible terms, how wind and water interact underground. The Nazca are perhaps better remembered for the enormous geoglyphs on the surface of that same plateau, whose function remains contested. It is possible that a civilization capable of engineering the puquillos was capable of rather more than we've credited them with. Between 1923 and 1951, a Latvian immigrant named Edward Leeds Kalnin, who stood 5 feet tall and weighed approximately 100 pounds following a bout of tuberculosis, quarried, transported, and assembled more than 1,100 tons of coral limestone into a structure in Homestead, Florida. He worked exclusively at night, alone, and was never once observed by a neighbor or passerby moving the large stones, despite sustained local curiosity. The largest single piece, a coral monolith he called the Polaris telescope, weighs 28 tons. A gate he carved from a 9-ton single block was balanced so precisely on its central axis that a child could swing it open with one finger. It operated that way for decades until its bearing wore out. When engineers disassembled the gate for repairs in 1986, they required a 50-ton crane and could not restore the original balance. Leeds Kalnin left no engineering notes, only cryptic pamphlets about magnetic currents. He claimed to have rediscovered the secret by which the ancient Egyptians built the pyramids. Whether that is the statement of a man who had genuinely figured something out, or the statement of a very private eccentric with an unusual aptitude for leverage and patience, no one who has examined the site has offered a fully satisfying mechanical explanation for how he did it. Sometime in the 4th century CE, a Roman glassworker crafted a cage cup now known as the Lycurgus cup, depicting the mythological king Lycurgus being consumed by vines. In daylight, the cup appears jade green. When illuminated from within, it turns blood red, a dichroic effect of unusual beauty. When scientists at the British Museum analyzed the glass in 1990 and again in subsequent studies, they found the explanation. The glass contains nanoparticles of gold and silver alloyed in a ratio of approximately 3.7, with particle sizes in the range of 50 to 100 nanometers. The optical properties of the cup arise from the interaction of light with metal particles at that precise scale, a phenomenon now known as plasmon resonance. As of 2013, researchers at the University of Illinois were exploring modern applications of the same technology for biosensors and diagnostic tools. They were working with equipment costing hundreds of thousands of dollars. The Roman craftsman who made the Lycurgus cup worked without a periodic table, without an electron microscope, and without a theory of quantum optics. He produced a single artifact that took the 20th century decades to understand, and that we are still finding uses for. It currently sits in the British Museum. Staff describe it as remarkable. What they do not explain is how a 4th century glassworker arrived at a nanoscale engineering solution that the modern world reinvented nearly 1,700 years later. Across 2,000 years and every inhabited continent, these 10 technologies reveal something that the standard narrative of human progress makes difficult to accommodate. The past was not simply earlier. In some domains, in some places, it was more advanced than what followed. Mainstream archaeology tends to treat these examples as isolated anomalies, brilliant flukes produced by lost geniuses in cultural vacuums, disconnected from any broader tradition of knowledge. Yet the consistency is difficult to ignore. Concrete that mineralizes rather than erodes, iron that passivates rather than oxidizes, glass engineered at the nanoscale. An analog computer with differential gearing, the same word, anomaly, is used to explain all of them, as if naming the exception relieves us of examining the pattern. What these technologies suggest collectively is not that ancient people were smarter than us, but that the accumulation and loss of knowledge is less linear than we prefer to believe. Entire branches of understanding, chemical, metallurgical, mechanical, were reached, applied, and then discontinued. The question is not merely academic. If these capacities existed and were lost once, they can be lost again. And perhaps the more searching inquiry is not how they built what they built, but what conditions allowed that knowledge to disappear so completely that we spent centuries dismissing the evidence of our own eyes.